Hello, my name is Gabriele Montefalcone. I am a third-year PhD candidate in the Weinberg Institute for Theoretical Physics at the University of Texas at Austin. Today, I will talk about some ongoing work with my advisor Katie Fries and Dr. Benjamin Wallish on the topic of testing neutrino properties using cosmological probes, specifically their free-streaming nature prior to recombination through its unique imprint in the cosmic microwave background. Before diving in, as every good cosmology talk, I have to start with a picture of the cosmic timeline of the universe, which I think shows very neatly the extraordinary advancements that were made over the past 50-60 years that led us to establish a consistent picture of essentially the entire cosmic history. We start with a hot thermal soup of all the particles in the standard model, perhaps dark matter, and as the universe expanded and cooled, it went through different phases, which I marked on top, significant events that ultimately led to the universe as we know it today. In this talk, I will specifically focus on the cosmic microwave background, this lingering radiation from 380,000 years after the Big Bang, associated with the formation of the first hydrogen atoms and the consequent decoupling of photons from the plasma. Today we observe these photons, about 90% of which lot scattered at this epoch. Over the last 20 to 30 years, observation of the spectrum of the fluctuations in this photon background have played a crucial role in establishing current model of cosmology. The richness of cosmological information contained in the CMB is second to none, but in this talk I will specifically focus on what the CMB can tell us about the condition of the universe in the deep radiation-dominated era, specifically with respect to cosmic neutrino. Similarly to what we just described in the context of the CMB, we also expect a cosmic neutrino background, which corresponds to the decoupling of neutrinos from the primordial plasma. This occurs at much earlier times, when the temperature of the universe was around 1 MeV. Unlike with photons, a direct detection of the cosmic neutrino background, due to the very weak interactions characteristic of neutrinos, is exceedingly difficult. Nonetheless, we've had indirect, though highly significant, evidence of the cosmic neutrino background for decades now. The cosmic microwave background has played an important role in providing such evidence and will continue to be one of the main probes to constrain and study many of the neutrino properties due to its high sensitivity to the radiation content in the early universe. In this talk, I will specifically going to discuss how we can use CMB data to constrain the free-streaming natures of neutrinos, and as I'm going to show, the imprint of this feature in the CMB is an especially robust probe to changes in model assumptions. As already anticipated, the CMB is the background radiation associated with the decoupling of photons from the primordial plasma. It approximately resembles a black body spectrum with a uniform temperature of 2.7 Kelvin and small spatial anisotropy roughly in the order of 1 over 10 to the minus 5, which are shown in this temperature map from the latest Planck satellite. The anisotropies in the CMB can be fully understood from the evolution of the cosmological perturbations prior to recombination. In fact, prior to recombination, photons, electrons, and protons were tightly coupled through Thomson and Coulomb scattering, forming what we call the photon-baryon fluid. In addition, initial fluctuation coming from inflation or other mechanism excited sound waves in this primordial plasma. And the acoustic oscillation were then driven by gravity. The physics of these cosmic sound waves is simply that of an harmonic oscillator with a time-dependent gravitational forcing as described by this equation in the center. At the most basic level, you have this photon-baryon fluid sitting in gravitational potential wells. There are the seeds of structure in the universe. As gravity tries to compress the fluid, the radiation pressure resists, resulting in acoustic oscillation with a characteristic sound speed of roughly square root of 1 over 3, as emphasized by this equation, where we see it's actually a little bit less than a third due to the added inertia from the baryons. Going back to our equation, we see that the source term is a combination of the Newtonian potential, which received contribution from all the components present in the early universe at a given time, mainly the baryons, photons, neutrino, and dark matter. They essentially all talk through gravity and in that way impact the evolution of the photon perturbation. So by solving this equation as expected, we just get acoustic oscillation, as already emphasized, which are schematically shown on this equation at the bottom, and where the cosine solution is the only one to survive under the assumption of the adiabatic initial condition, which is generically a prediction of inflation. The evolution of the cosmic sound wave as captured at the moment of last scattering is exactly what we observe in the CMB power spectrum. Not only in the temperature power spectrum, which is what I'm showing here on the top left, but also in the polarization power spectrum on the top right and the cross-correlation between temperature and polarization. To gain some intuition, the temperature power spectrum essentially traces the density perturbations. In this sense, the first peak location is a direct measurement of the angular size of the distance traveled by the sound waves, the so-called sound horizon at decoupling, and then we literally just see the harmonics of it. With respect to polarization, the CMB photons can acquire net polarization only from a gradient in the velocity field. Once the photons have already acquired an appreciable mean-free path just before they decouple. And in this sense, we can think of the polarization spectrum as tracing the velocity fluctuations. So we expect it to be correlated with the temperature power spectrum and out of phase, which is emphasized by the sine square dependence compared to the cosine square dependence. And finally, putting these two together, the cross-correlation of the temperature and polarization roughly tells us how the plasma is moving in the gravitational potential wells. And overall, these are really the primary signals that we are measuring when we look at the CMB, and that it provide us with information regarding the content and evolution in the early universe. Going back to neutrinos, in the early universe, they make up roughly 40% of the radiation density, the rest being in photons. We typically parameterize it in terms of this equation on top, where we write their contributions in terms of the photon energy density, as well as the parameter N effective, normalized so that in the context of the standard model, it would be equal to 3 if neutrinos decoupled instantaneously. To be exact, the standard model value is now 3.044, where these additional digits also account for flavor oscillations and finite temperature corrections from QED, now up to third order with this latest work by Akitala and Yamaguchi. Now, given that in the early universe, the relevant energy density is essentially all in radiation, these cosmic neutrinos will leave a sizable gravitational imprint in the CMB, which we can use to constrain their properties, both in terms of their energy density and the nature of their perturbations. The latest constraints from CMB data, specifically Planck 2018, find that N effective is consistent with the standard model expectation of 3. Now, I want to move on to describe more in details what the gravitational effects of cosmic neutrinos in the CMB power spectra actually are, and what properties of neutrinos they allow us to probe. Now, the first main effect comes from the background energy density of these neutrinos, which alters the Hubble expansion, consequently affecting the dumping tail of the CMB power spectrum. We see here that the greater the value of N effective, the more dumping we get in the CMB. If we keep the first peak or the angular size of the sound horizon fixed, which is generically done since that is a quantity extremely well measured in the data. Now, it is important to note that this is a background effect and has degeneracy with many other cosmological parameters, most importantly with the helium fraction. In fact, since helium has a much larger binding energy than hydrogen, increasing the helium fraction for a fixed baryon density, which is also well determined by the relative peak heights of the CMB, this will decrease the number of free electrons at the time of hydrogen recombination, resulting in a larger photon mean-free path and in consequence more dumping. So this is important because if we want to measure the primordial helium fraction independently from BBN measurements, this degeneracy will be one of the main limiting factors in constraining the N effective in the future. Now, standard model neutrinos are also free streaming in the early universe after their decoupling, and by doing so they induce metric perturbations ahead of the sound horizon. You can clearly see this by the animation on the right, where the neutrinos are in green and their perturbation peak is ahead of the photon baryon fluid, essentially pulling such perturbations, shifting their peaks to larger radii. So, if we compute the effects on the CMB power spectrum, we see a number of changes, particularly a phase shift. Roughly speaking, the cosine solution we saw earlier for the cosmic sound waves acquires an additional phase. In particular, as illustrated in this right figure, if we increase N effective and hence the number of relativistic degrees of freedom, the peaks of the CMB power spectrum in temperature move to larger scale and hence smaller multiples. Now, the size of this effect is quite small, as emphasized by this approximation. But nonetheless, it was already detected quite a few years ago by Folin et al. In 2015 using Planck 2013 temperature-only data. What is particularly interesting about this effect is that assuming adiabatic fluctuations, such a coherent shift in the CMB power spectra can only be produced by free streaming radiation, with the only alternative being isocurvature fluctuations. This was shown rigorously for the first time by Baumann et al. In 2015, and what this means is that the phase shift is really a pristine signature of the free-streaming nature of standard model neutrinos. Said differently, if neutrinos were not free-streaming in the early universe due to, for instance, sizable self-interactions or some non-standard interaction with the dark sector, this effect would not be present in the CMB or would be of much smaller in size. A major role in improving our measurements of the phase shift in the future, and hence our understanding of this key property of standard neutrinos, would be played by polarization measurements. In fact, as shown in this figure on the right, the same shift that we saw in the temperature power spectrum also appears in the polarization spectrum, which actually provides a cleaner signal, given that the peaks and troughs of the polarization spectrum are really a snapshot at the very last scattering surface, in contrast with the temperature spectrum, for which the last few scatterings are relevant, with the effect of smearing out the peaks and troughs. We can measure the size of the phase shift as a function of multiple and introduce a new parameter n delta phi effective, whose only job is to shift the perturbation spectra according to this template that we just extracted, FL, and more specifically to this formula, where essentially FL represents the phase shift as normalized to a specific number of neutrino species, and this amplitude is supposed to take care of this normalization. This corresponds to the original method used by Folin et al. In 2015, which is also what we're following in our current work. Our contribution to the original framework was also to consider the polarization power spectra in the template extraction, both their autocorrelation and cross-correlation with temperature, as well as introduce a new, more physically motivated analytic form of the template, which asymptotically approaches a constant at high multiples, which is exactly what we expect for the phase shift for modes that enter the horizon deep in radiation domination, whereas at low multiples corresponding to modes that even enter the horizon during matter domination, the shift approaches zero as the radiation density is becoming more and more subdominant, diminishing drastically the effect that neutrinos can actually imprint. Now, moving on to data, as already mentioned, this phase shift was detected in the temperature data by Folin et al. with a value of n delta phi effective greater than 0 at more than 5 sigma. In this analysis, what we're assuming is that n effective is equal to the standard model value from neutrinos, so that n delta phi is effectively measuring how free streamings are neutrinos. And we see that the result is consistent with all of the 3 species being free streaming. What we've done now, and this is still preliminary result, is to look at Planck 2018 data, just in temperature, and that's the gray curve on the right, which is already somewhat more constraining, but not by much. When we include polarization data, which is the blue curve on the right, we do get a sizable improvement in the constraint, as we would expect, not only because of the added data, but again, due to the sharper peaks that characterize the polarization spectra. And finally, when adding ACT and SPT data, which is the red curve on the right, we get an additional decrease in the error bars by roughly 30%. Looking ahead, we also ran some forecasts, and we see again an improvement of roughly 30 to 40% for SO and another factor of 2 for CMB S4. And these improvements, starting already from the addition of ACT and SPT and also this upcoming CMB experiment, are simply a product of measuring additional peaks at higher and higher multiples, especially from the polarization spectra. In addition, we can ask the question, what if we vary n effective away from its standard model value of 3? Effectively asking about any possible contribution to the radiation density in addition to the photon. And that's shown here on this plot, with n effective on the x-axis and n delta phi effective on the y-axis. And again, we see that the data are consistent with 3 neutrino species all free streaming at roughly the 1 sigma level. In addition to the standard analysis, we have also looked at a different way of extracting the phase shift, not based on the CMB power spectra, but instead at the level of the perturbations, which is where the phase shift is actually imprinted, as we saw previously in the delta gamma, which described the photon perturbations. This would provide a cleaner way of extracting this observable, avoiding projection and smearing effects. In a nutshell, the temperature and polarization power spectra are ultimately determined by their corresponding perturbation sources after being projected to harmonic space and integrated up to the surface of last scattering. Here I'm showing some of the components of both the temperature and polarization sources that experience a phase shift induced by the neutrino perturbations, emphasizes in green the photon perturbation component that we have mainly focused on so far. In the figure, I portray the phase shift in the perturbations, specifically at the time of recombination, in the most relevant components of the source terms. Of course, a shift is imprinted throughout the cosmic history, so we have to extract the corresponding phase shift template as it evolves over time. In this left figure, I'm showing some bins in redshift, which once we have this template, which can then use it to shift the perturbation signal, which in turn will shift the output CMB power spectra. When we do this and we measure the resulting phase shift template at the CL level, we see that the spectrum-based template used so far and our new perturbation-based approach are consistent. And this is emphasized by the plot on the right, where we clearly see the two fits: in solid, the spectrum-based method, and in dashed, the perturbation-based method. Looking closely, one can note a very minor discrepancy. Specifically, the spectrum-based approach seems to slightly overestimate the induced phase shift, particularly at larger multiples. Again, this difference is statistically irrelevant, but we're currently working on honing down the source of the discrepancy, which could give us some insights on the benefits that the more direct perturbation-based method will provide us in terms of constraining power, particularly in the context of a coming CMB experiment. Now, when confronting this method with data, we see that relative to the original spectrum-based template on the top panel of the figure on the right, the results from the perturbation-based template on the bottom panel of the figure are consistent at the 1 sigma level, with the central values of n delta phi that are roughly 10% smaller than the spectrum-based template results, but that overall are still compatible with all 3 neutrino species being free streaming. These two tendencies are also confirmed when we let an effective vary away from its standard model value of 3, where again we see that also using the more direct perturbation-based method to extract the induced phase shift, the data are consistent with 3 neutrino species, all free streaming at the 1 sigma level. In summary, in this talk we've explored the relevance of CMB measurement in constraining the properties of cosmic neutrinos. In particular, I presented new data analysis and forecast for the free streaming nature of neutrinos. And it looks like from the induced phase shift that we measured, the neutrinos are indeed free streaming according to the standard model, which in turn sets important constraints on non-standard neutrino physics, such as the strength of possible self-interactions or other interactions with the dark sector or other components in the universe. Finally, I want to highlight our new method for the phase shift extraction directly at the perturbation level, which provides a cleaner way to extract such observable, which may become particularly relevant with the forthcoming improvements in our detectors, a subject we're still currently exploring by running forecast also with this new methodology. And with that, I thank you and I look forward to our discussion.